pull back,
There you
switch
go.
back.
Let's put more down just in case we need it later.
Okay, we are here.
Slack in there.
Are we set?
Do you want to do any intros or anything?
Sure, absolutely, it's time.
We can turn off some lights too. There's another, where's the other microphone?
Hi,
So much. Thank you so much for
you're very welcome,
the time and
I had
really
two
appreciate
microphones
that.
a minute ago.
very welcome.
Well,
We are excited to,
Other thing like that.
have you present.
Oh, thank you. I've given this presentation in Cincinnati, along with a couple others on
that's
Mars.
like living without drugs.
It's like being catapulted back
You
in
don't
1990.
exist if you don't have your phone.
Like the early 2000s.
Well,
There was a news
Lost my other microphone.
some women who went out,
You're not a real person.
did it on purpose, left their phone at home for the whole day. Felt like she was missing drugs.
Another little guy, that's just like that. But anyway, you can talk into that one. So.
Can you hear me now?
Can you hear me now? Sure.
Can you see me?
Yeah.
Hey, everyone. Good evening. Welcome to the February general meeting of LAS. I would like to introduce Terra. Most of you know her very well. She's going to present, she will talk about geology of Mars, right? And we are all excited to have her present. Before we move forward, I would like to ask, is anyone here the new member? Hey.
Mars, but I've never been to a single meeting before. I've volunteered like 2 or 3 times. Thanks, Joseph.
I would like to go through the board members and ask them for the updates. Tom, would you like to
Sure.
provide some updates on?
Well, the biggest update is that we are moving this venue. Apparently, there was a new person in charge of the place, and they decided to charge us money for doing this instead of doing it free. So I dug around and I got my church to agree to let us use their youth center, which is a bigger room than this. It's got a video projector.
Too old for a youth center?
It's on, it's in Anchorage. It's not too far. It's a little bit south of the UAC. So it's, you know what the UAC is? It's not far out. It's Epiphany Catholic Church. And I'll send an email out with maps and all that fun stuff. So starting next month, we'll be there for free, which is good. Do we want to talk about this wonderful thing with the, that's been going back and forth about the,
About the live streaming?
no, well, that film about, what are we doing?
Yeah, sure. I think it's not finalized yet, but if you would like
Where,
to.
when, A, do we want to do it? And if so, do we want to pay money or do it for free or?
Sure. Pat, do you want to
Yeah,
provide some updates on
I
that?
don't think we should pay for anything.
Alright.
But my thinking was when I sent that out about EP Sawyer was to take it to EP Sawyer and see if they want to do it. And they can charge money for it if they want to. And we would provide them support, and then we have the Dark Sky folks who could provide support. And see if EP Sawyer wants to run with it, because in the past they've said they wanted to do like a speaker series type thing and have us provide a program for one of those events that they had talked about. They want to do things out there, and I think we should pass this to them. What is it? You don't read emails anymore? No, this is off of the board. It's a movie type thing, I guess, a documentary about
Dark
dark
Sky.
skies. And you can arrange screenings of it and, but you have to pay for this.
There you go, hold on.
And you have to pay for the screenings for it. But, EP Sawyer has said many times he'd like to have events out there. And instead of us doing it, we should maybe send it to them because it's their site to begin with. And we're not gonna pay $500 to rent this building. And then another $150 if there's less than 50 people, or $600 if there's more than 50 people. You know, so it's something I think EP Sawyer might really be interested in doing. Because they've expressed that interest in the past, instead of us, you know, saying, yeah, we'll talk to them, say, we want to do it. I think we should just pass it off to the state. And I'm 90% sure they'd be interested in it, because they don't have to pay for the building. You know, it'd be $150 roughly, or $600, something like that, and they could charge admission if they wanted to, or they could just do it. So that's what my thinking was, as opposed to us getting directly involved with the screening. And this, back to Tom.
Well, this video we're talking about is about dark sky, and I have no idea how long it is, if it's a feature-length film or 20 minutes or what have you. But
An alternative to that would be U of L has those PAL programs.
Yeah.
And I thought, you know, maybe they might be interested in having one of those presentations out there.
So this is a movie that's already done?
yes, it's a documentary. Apparently, it's aired on PBS.
Okay.
And they're looking, LAS got an email from this production company saying, would you like to do this, and blah, blah, blah.
Get a crowd together.
Yeah.
And it could draw a pretty nice crowd, you know, probably more than what they could handle up at Monarch. And it's a lousy place anyway, you can't see half the time.
Especially if you gotta carry a scooter up the stairs.
Yeah. I know. So that was my thinking, since I opened up the can of worms.
Or foot damage from parachuting.
All right, yeah.
All right, so much.
So, yeah, Tara, you can just. So, once we are done with the, I think, do you have this connected over here? Okay.
Yeah.
Yeah,
It just-
at the end, we'll go for, you know, the update for Kirby, but I think, yeah, we'll do that after the meeting if we can, you know.
Well, I was just gonna say,
Okay.
for those who don't know, we have built a concrete pad platform for our 20-inch obsession. And that 20-inch obsession and the 15-inch Discovery, the mirrors have been shipped off to Spectrum Coatings, and they're gonna be recoated. So we should have those back hopefully next month, but it may not be till April, but I don't know exactly when they'll be back.
How much did that cost?
About $1,000 for both of them.
Not bad.
So for all four mirrors, so that's not bad. And then we have ordered a shed, an 8x12 shed, that's gonna be on the end of the platform, that will store that 20-inch obsession in and get it out of the multi-purpose buildings, because it takes up a lot of room. And then we're gonna run electrical from the dome over to there, and then we wanna run an Ethernet cable from the dome to the observatory, because we've had problems with we're getting that Wi-Fi inside there, and it's just the distance, and the access point is not a very good piece of equipment, and it costs us more to replace that than would be just to dig a small trench and run a Ethernet cable out there. So we're looking at trying to do all of that all at once, so that'll be next month or April, sometime in
Okay,
there.
cool, pretty cool. Thank you, Tom. Thank you, Ron. All right.
Here, have the mic.
I've got one.
She's
Right.
It's up to you.
Ready?
I'm ready.
Rock and roll.
Ready to rock and roll. You can all hear me. Can we make the lights a little bit dimmer? Is it on a rheostat or? Because there's a lot of glare on the screen. I've got some detailed slides here you're going to want to be able to see.
Are you talking about you want it to be a dark sky in here?
Dim is, I guess it's gonna go.
You're probably turning the lights down in some room.
Well,
And you can't turn off that middle panel?
Somebody in Germany's gonna call up and say, hey,
That's as
cut
down
it out.
as it's going. Unless we turn them off.
Can you turn off the middle panel?
No, I've got that circuit and that circuit, that's it,
Okay.
and the screen control. But it's new.
Just push the button.
Or turn them off.
Just go ahead.
Yeah, turn them off, whatever.
I do off.
I think that's good. I think we'll be able to see better. It's all right, I will enlighten you, I promise.
I'm just gonna do this.
Hi, I'm Terra Clark. I am a geologist. I'm retired now. I was a consulting geologist for the last few years in energy resources, primarily oil and gas. Also some lithium brines and a little bit of uranium work. But that's all behind me now. I left Cincinnati. I've moved here to be closer to family. And so I'm going to talk tonight about the geology of Mars. A friend of mine up in Vermont, I told him what I was going to do, and he said, I didn't know you were a Mars geologist. I said, I'm not a Mars geologist. I'm very much an Earth-based geologist, but I've had a lifelong interest in the red planet. And so this kind of carries over to some of my sideline research that I do just for pleasure. And so I put together a general talk tonight on the geology and geologic history of Mars. Well, appropriately, it all starts on Mars Hill. And that's me, some years ago, standing by the tomb of who? Percival Lowell. Percival Lowell. Up in Flagstaff, Arizona. Percival Lowell was from Lowell, Massachusetts, very wealthy family, schooled, I think, in the classics and in mathematics. He really wasn't schooled as an astronomer, but he was interested in it for most of his life. He established Lowell Observatory in 1894 with the goal of studying the great opposition of Mars that was going to take place between 1898 and 1899. This, by the way, is the same great opposition of Mars that inspired H.G. Wells to write his book, War of the Worlds. So when he spoke of us being scrutinized, we were being scrutinized from Mars. Well, tonight we're going to scrutinize Mars and look in the other direction. Lowell wrote his famous landmark book, Mars and Its Canals, back in 1906, and it's still quite interesting, although it's almost entirely wrong. Well, if we look at Mars, we see, first of all, that it is divided basically into two provinces geologically. We call this the Martian crustal dichotomy because the division of these two prominences is largely the result of elevation. There is the southern portion of Mars, which is much higher than the lower portion. So we have the southern highlands and the northern lowlands. Vastitas borealis, which means the desolate north. And then you see the southern highlands, and almost all the features of interest are in the southern highlands. In general, Mars lacks any clear evidence of the Earth type of plate tectonics as we know it that shaped our surface. This has not happened on Mars. Crustal differentiation and the resulting first-order relief features, such as mountains, plains, and plateaus on Mars, are much more like what we would have expected on the early Earth before plate tectonics really got going, and the geography became more and more differentiated by that process. If we look at Mars in terms of a deformational model, it very much fits what we call in tectonics and in basin analysis and in oil exploration, which I've been involved in. It's a thin skin type tectonic deformational model. If we compare Mars and the Earth in terms of their internal structure, we see similarities, but we also see some significant differences. For one thing, the size of Mars's core proportional to its planet is much greater than the size of the solid core or inner core of the Earth. Mars itself is much smaller than Earth. As you can see, these two diagrams are drawn proportionally to one another and to scale. You can see that Mars has a fairly simple internal structure. With the core, we're not certain if it is solid or liquid. The Earth has a solid inner core and a liquid outer core. We're not certain as to the constituency of the core of Mars. We do know that the density of the core from gravitational studies is about 20% less than the density of Earth's core, and we think that this is because the Martian core consists of iron. Earth's inner core is iron, nickel, and hydrogen. We think that the Martian inner core is primarily iron, sulfur, carbon, and oxygen, which accounts for the lower density. If we look at the mantle structure and the crustal structure of Earth versus Mars, we have much less of a discrete, well-differentiated crust upper mantle situation on Mars. On Earth, we have the oceanic and continental crust, which are different from one another. These are both part of what we refer to as the lithosphere, which extends down to about 100 kilometers and attaches itself to a thin upper semi-rigid skin of the upper mantle that we call the asthenosphere. There is no real lithosphere or asthenosphere as far as we can tell thus far on Mars. It is a basaltic crust, thicker than the oceanic crust of the Earth, which is primarily a basaltic crust, sitting on a plastic viscid mantle. Also, from what we know, we don't have the kind of convection cell activity rising up off the core and moving through the mantle on Mars that we do have on Earth. For Earth, this is very important to us because the fluid motion, those convection cells not only drive plate tectonics and cause continental divergence and convergence, but they also, and the birth of ocean basins, but they also drive Earth's magnetic field. Mars has a much, much, much weaker magnetic field. It has almost completely died out. We do know that it existed in the past from studies of residual magnetism in the southern highlands and the northern lowlands, the southern highlands being much more magnetic than the lowlands on Mars. But still, there is no real geomagnetic or global magnetic type of field system on Mars like we have on Earth, which means also that there is no exosphere magnetic field or plasma magnetic field like we have on Earth at this point, and hasn't been for a very, very long time. And that's primarily responsible for Mars' loss of most of its water, much of its atmosphere, the development of its perchlorates and its soil, and so forth. In terms of large-scale surface expression of the internal processes on Mars, they primarily consist of deep-seated upwelling of mafic or very dense, high iron and magnesium type rocks, moving up from the mantle to the surface, rising through hotspot type volcanic activity and producing large shield volcanoes on Mars. We don't see any of the kind of stratovolcano type development that we find in island arcs and subduction zones on Earth, on Mars. It doesn't exist. There's no plate tectonics to produce it. On Mars, we also see extensional or normal type faulting with downdropped blocks as opposed to upthrown blocks. And typically what we have developed are rift valleys, the largest of which is the Mariner Valley, where we have normal faults that dip towards one another with a downdropped intermediate block and crustal extension extending out laterally in opposite directions from the axis of that activity. Because of that, and because, of course, the surface area of the planet isn't getting any larger, we have to have compensational flexure type folding to take advantage of or to compensate for the crustal extension that's going on with the faults. In addition to that, we also have compressional faulting in the form of thrust faults, mostly blind thrust faults on Mars. The most predominant activity on Mars is volcanism, though, volcanic activity. And the really extensive areas in the Tharsis Rise, this area here, this arc of volcanoes here, the largest of which is the largest volcano that we know of in the solar system, Olympus Mons or Mount Olympus here. So we have a volcanic arc consisting of Olympus Mons, Alba Mons, and Tempe Terra here, the Tharsis Rise here, chain of volcanoes, predominantly 3 volcanoes along what appears to be a rift system here, and then the Valles Marineris or Mariner Valley here, which has developed an association to this absolutely enormous volcanic pile in this area. We also have additional volcanism over here in Elysium Mons and in Hesperia Planum. Here you see Olympus Mons. It's just this absolutely massive shield volcano with a huge collapse caldera here. And then we see this rift consisting of 3 additional shield volcanoes just to the east of the Tharsis Rise or the Tharsis Bulge. Here you can see all of this fracturing under a lot of this weight, and here you see the Mariner Valley. Olympus Mons, absolutely enormous, as big as the state of Nebraska, 35 miles high, approximately. I mean, there's nothing else like it in the solar system. Here you can get an idea of the size of Mount Olympus here in comparison to Mount Everest on Earth, which is not a volcanic mountain. It's a block fault mountain, and Mauna Loa, Mauna Kea in Hawaii. So this is very, very much like a giant version of this. Going back to this, when you look at this, kind of think the Big Island of Hawaii. It's very much like the Big Island of Hawaii, although it's even bigger than the Big Island. The Big Island of Hawaii consists largely of Mauna Loa and Mauna Kea. You might also think of the Deccan Plateau in India and the Columbia Plateau in the Pacific Northwest, where you have over 2 miles of accumulated basalt flows. So why is it so big? Why does Mars get to have the biggest volcano when it's the planet that's only about half the diameter of the Earth? Well, that's part of it, because Mars is smaller. Being smaller, there's less gravity on Mars. It has a less dense core. The mantle material has approximately the same density because it's made of the same olivine and pyroxene type minerals as the Earth. It has a basalt crust, but overall, the total mass is much less, and of course gravity is a force, mass times acceleration. And so lower gravity, and this results in less isostatic depression of the crustal mass of Mars, large objects on Mars like Olympus Mons, down into the mantle. Think of kind of an iceberg riding in water. There's an isostatic equilibrium that exists between the mass of that ice, which is about 9/10 the mass of the water that it rides in. So we have something similar to that. It's called isostasy. And with Mars, it has less capability to allow the mass to sink down because there's less gravitational pull pulling it towards the center of the planet. With less gravity, there's less weight. Weight is force. So the mountains don't compress under their own weight nearly as much. With less gravity, there's less potential energy. With less potential energy, there's less kinetic energy for erosion to do work leveling the higher surfaces of Mars. And since Mars lacks plate tectonics, the crust isn't moving laterally over a mantle plume. So when you look at the big island of Hawaii, it's sitting over the current hotspot. Now the current hotspot is down near the southern edge of the big island, and that arc extends all the way to Midway Island over 2,000 miles away. The crust, the basalt crust, has moved over that mantle plume, and as that has happened, the volcanoes as we see them appear to be smaller because they're older, they're more eroded, and they've also sank back down more into the crust or into the mantle because of cooling and contraction and increased density of the volcanic material. So Mars lacks that. Olympus Mons is sitting over a hot spot on top of a mantle plume, and it stays there. So just think of what Hawaii would be like if there was no movement off towards the south. Look at making the arc appear to be moving towards the northwest. In terms of large-scale structural deformation, when we talk about structural deformation, we're talking about folding and faulting. With Mars, most dominantly, it's extensional faulting. For the most dominant tectonic feature that we see as a result of structural deformation on Mars, it's the Mariner Valley. And this is a direct result of extensional faulting. The Mariner Valley region consists largely of two parallel fault trough zones. These are dominated by trough parallel normal faults with the component left lateral strike slip transcurrent motion in conjunction with the dip slip movement. The Mariner Valley fault zone is basically a trans-extensional fault similar to the Dead Sea Rift on the Earth. And I'll try to give you Earth analogs as we talk about all these things. So in terms of the general geology, we see basically all kinds of in echelon normal faulting running across the Mariner Valley. Here's another area up in here, a northern extension of the Mariner Valley, another trough here. And these are stepped or in echelon. And then at right angles to that, we see the work of compression producing these compressional folds. Here you can see the upthrown blocks, down-dropped, upthrown, down-dropped back in here, and so forth.
Tara, are these photographs or where is this imagery coming from?
Both. These are, of course, cartographic products produced over images. So everything that you're looking at, for the most part, are actual images from either Mars orbiters or which we've been doing since, before Viking, 60 years, and other probes. But a lot of the stuff like this has been enhanced and also, of course, drawn on, so it's a cartographic product. Here you can see one of the main faults running along this side of the Mariner Valley. You can see another rift zone over here. You can see that this is has a left lateral strike slip component. Here's a large impact basin here that you can follow over to here, and you can see if you look across the fault, it's moved across to the left, like so. So the offset rim of this old impact basin, you can see about 150 kilometers of transcurrent motion, strike-slip motion to the left.
What's the time frame for that? Do they know?
What?
The time frame for that to happen?
We'll get to it. You got to be patient.
Okay.
You got to. We're going to go hit the history after we hit the basic features. Okay, so formation of the Mariner Valley is closely tied to the formation of the Tharsis Bulge, as we said. It's that enormous loading in that one portion of the planet. The volcanic loading of the crust continued on a vast scale with the growth of Tharsis, which has continued almost to the present, maybe to the present. We have an idea that there's still some volcanism going on in that area. More volcanism results in loss of isostatic equilibrium, increased load here, sinking down, extensional faulting to accommodate it. The load became so great that it just couldn't support itself, and this led to a widespread flexure, followed by fracture in the elevated regions of Tharsis, and then working its way towards the east. When the crust finally failed to hold up, Tharsis's extensional fractures formed, and eventual subsidence and displacement produced the Mariner Valley and its associated terrain as we see it today. Here you see it. Here's the Mariner Valley. This is Tharsis. This is Olympus. This is a massive outflow channel that we'll be talking about here. So this is erosional. This isn't a fault feature. Wrinkle ridges. Wrinkle ridges are corresponding structural folds that have developed on Mars. Here you can see a series of them. In some cases, they're stepped in echelon folds. Some cases, they're parallel. Some, they're curvilinear. The wrinkle ridges are low, sinuous fold ridges that can extend up to several hundred kilometers. They're the result of compressional stresses in the Mars crust with flexure folding compensating for extension elsewhere, the thin skin tectonic model we've been talking about. They tend to run transverse to the extensional faults. They are thought to occur above underlying blind thrust faults where a block is pushing laterally over an underlying block at a very low angle. It's a blind thrust because it's buried, it's covered. They're the result of the buckling of the overlying basaltic layers. In addition, it is flexured, and we think it's produced what we call a décollement. Décollement is similar to carpet wrinkles. What happens when you have a décollement kind of structure, the upper lying layer detaches more or less completely from the lower lying layer. We see this in certain areas of the Alps, like in the Jura, and it slides, and as it's sliding forth, it wrinkles, kind of like you would expect to see if you slid your carpet, if you pushed on one end of your carpet and let it slide over the floor. Here you can see the transverse wrinkle ridges, here, 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 running all across through here. Look at all of this. And here's the main trend of the Mariner Valley. And I should mention, if we superimpose the Mariner Valley over a map of the United States, it would go from the East Coast to the West Coast. So, yeah, just a little bit bigger than the Grand Canyon. In the Tharsis region, the wrinkle ridges run transverse to the trend of the major faults that have produced the Mariner Valley. They're also common in Hesperia planum, Solus planum, and the low-lying plains of Crisi planatia and the Elysium planatia. Some of the ridges are straight, parallel, regularly spaced, as I mentioned. Others are irregular, some are curved. circular or stepped or in echelon. Here you can see some in echelon. See how it steps off. Here's a geologic map of that area of Mars. This would be larger. It would be about the size of a geologic map of North America. So we're covering a lot of area. Here is the Mariner Valley. Here's Tharsis, Olympus. And you can see the trend of all these wrinkle ridges, all of these folds. Now, in terms of history and time, all of this goes back to the inception of the inner terrestrial planets around 4.5 billion years ago. Here you see the moon, here you see Mars, here you see Earth. Mars is divided up into 3 eons or eras: the Noachian, the Hesperian, and the Amazonian. The Amazonian extends up to the present and goes back 1.8 billion years. So it's a very, very long period. By comparison, this is the Phanerozoic, beginning with the Cambrian, just this little area here. So this is the Paleozoic, the Mesozoic, and the Cenozoic. This is organized life, basically, on Earth. These are invertebrates and vertebrates. So a lot of time in the Amazonian, a lot of time in the Hesperian, a lot of time in the Noachian. The late heavy bombardment, which greatly affected all of the planets in the inner solar system, the moon, the Earth, and so forth, is a major event in early Earth history. That is occurring around this time here on Mars, around here on Earth, from around 4 billion years up to around 3 billion, with most of it between about 3.5 and 2.8. Huge impacts. There's also a major oxidation event. The Great Oxidation Event took place on Earth right around here. With Mars, Mars also is a very oxidizing environment. It started oxidizing much, much earlier. We're not even certain if there was ever a reducing environment geochemically on Mars. I guess you'd say geochemically, marsochemically. If so, it existed in the Noachian. So Mars geologic history begins with the Noachian era. Goes from the earliest stages of Mars geologic history, when the planet is being shaped by large impactors. Like the moon during the ancient impact-rich Nectarian Embrian period that created the Embrian basin on the moon. This is coinciding with the late heavy bombardment in Earth's pre-Archean history, what we call that the Hadean on Earth, the very beginning of Precambrian time, deep, deep time. Big impacts occurring at the same time on Mars. These early impacts in the solar system, as I mentioned, occurred primarily between 4 and 2.5 billion years ago, but mostly between around 3.9 and 3. And we see the consummate work of this. We see massive impact basins on Mars. The Hellas Basin, for example. The Idris Basin here. The Argyre, and so forth. The whole lowlands area, the Great Crustal Dichotomy, may in itself be the result of massive, very, very early impacting. We see a similar kind of thing on the moon, the lunar highlands and the lunar lowlands. So following this, we have these impacts like that produce basins in Hellas, Argyre, Utopia. The very last impact, we think, major impact, was here. just off of the Utopia Basin, just south of it. Major volcanism was happening during the Noachian. This is when the Tharsis Rise started to develop by the middle of the Noachian era, although it may have even started earlier than that. So in the Noachian era, water was present in significant amounts on both the surface of Mars and in its atmosphere. Mars had a much denser atmosphere. It had a hydrologic cycle. It may now, we think, even have had an ocean in the northern lowland area. It was initially suggested that the source of water on Mars and on Earth was from the result of very early cometary impacts and planetary accretion. Most people don't believe that anymore. Most thought now is that the water on Mars and the water on Earth came from internal rather than external sources through the fractional crystallization and magmatic differentiation of rocks in the interior. All you got to do is look at volcanoes. They produce lots and lots and lots of steam. And that's not just subduction zone volcanoes where your steam sources are coming from salt water, connate water in the sedimentary rocks that have been dragged down into the subduction zone. You get lots of water from shield volcano eruptions as well. In fact, I was just talking to a friend of mine, Tim Parker, who's a Mars geologist at JPL. He's just retired, and Tim was confirming what I just said about the internal rather than the external source for Mars water. The action of these Noachian waters, aside from perhaps producing an ocean in the northern lowlands, extensive valley networks were formed. These laid down deltaic deposits and alluvial fans in lower areas. Sedimentary material was derived from weathering and erosion in a much more active atmosphere, bringing material down and depositing in lowlands. So the older, higher areas are being worn down, and they're contributing to a veneer of sediment in lowland craters and impact basins. The result then is, like on Earth, a smoothing out of the intercrater plains as a result of erosion and deposition of water-laid sedimentary deposits, just not nearly to the effect as it has taken place on Earth, because we've had a hydrologic cycle since we've had a planet. Here you can see evidence of these Noachian valley networks and dendritic drainage systems. Here you can see all this runoff coming down from this highland area. All of these interconnected tributaries. Nice dendritic drainage, bringing sediment down into this impact basin here. The next era, the middle era, is the Hesperian era. And the Hesperian era begins with the decrease in extramartian impacts. The major impacting is over now, and there's an increase in volcanic activity and crustal loading and extensional Rift Valley faulting and consequent wrinkle ridge development. There also appears to be a decrease in the amount of water present on the surface of Mars. The atmosphere, the oceans are boiling off. Mars has lost its magnetic field, has no geomagnetic umbrella protecting it like Earth has, and so the atmosphere is now about 1/100th the density of Earth's atmosphere, virtually a tiniest fraction of water. It appears the normal hydrologic cycle ceases to operate in the Hesperian. Water availability becomes very episodic, and we have periodic catastrophic outburst floods through massive outburst channels or outflow channels that develop as vast amounts of water is periodically released, probably from sudden melting of glaciers and breaching of ice-filled dams, much like what we've seen at the end of the Pleistocene here on Earth, for example, with the formation of the Channel Scablands. So we have these huge outflow channels and associated alluvial fans developing, creating these enormous scars similar to the Channel Scablands in eastern Washington. And here you can see an example of these things. Look at this, it's just enormous, this giant rhomboid bar type system. These things only form with catastrophic floods, huge volumes of water released very, very quickly. Here you can see outflow channels emptying into the northern plains of Chrysoplanacia. Here's the Kasai Valley, the largest outflow channels on Mars. Kasai Valley again, actual image, not a photograph, but an image, electronically scanned image. Big rhomboid bar development, huge oxbows swinging around this obstruction here created by this crater rim. Another outflow channel here. You can see this developing in the lee here. The most recent era is the Amazonian. That goes from about 1.8 billion years ago up to the present. Third most recent. The floor of the northern lowlands is being infilled and covered by smooth sedimentary deposits on top of the basalt, producing vast northern plains known as the Vastitas Borealis, or the northern wasteland, the northern desolation. Vastitas means desolation or devastation in Latin. Becomes a much quieter time geologically as we go into the Amazonian, although volcanism continues, but at a slower pace than it had been. Notable exception is still major building on Olympus Mons. Much of Tharsis has slowed way down, but Olympus Mons is just developing and developing still. Continuing volcanic activity then is characteristic of the Amazonian, especially around Tharsis. Massive hotspot outpouring of basalt produces the largest mountain, Olympus Mons, although that has started long before, but as we see it today is largely a result of the Amazonian. Gradual loss of water, lessening of fluvial activity, diminishing of an atmospheric greenhouse as the atmosphere basically boils off into space without a greenhouse. There's nothing to trap outgoing infrared radiation, and so the temperature falls to a much lower Stefan Boltzmann constant temperature. Ensuing desertification, increasing periglacial activity. Periglacial activity is associated with frozen ground, not glaciers, but frozen ground. It would take place on Earth in tundra areas. Wind action, mass wasting, dominant surface shaping processes. So mass wasting on Mars, this is gravity-driven movement of materials over the surface from higher areas to low areas. Here you can see a 2019 high-res camera image from the Mars Reconnaissance Orbiter capturing these rock falls, these big talus debris slides coming on down off of this highland area. This escarpment is a fault line. Huge landslides in the Mariner Valley. Just look at these big arcuate scarps. Just massive, these big slumps. These have curved glide planes where the blocks, typically imbricated blocks, several, one on top of the other, slide over one another and down. You can see the landslide deposits, the debris, all crumpled. See slumping here along the walls of the Mariner Valley, and up here too. Carrying material down into the valley floor. This is a massive slump right here. Look at, you can see 1, 2, 3, 4, 5, 6, 7 imbricated slump blocks. And look at the run out. The toe.
What's the scale on that picture?
The toe on this, well, it's the Mariner Valley, so we're probably talking 100 miles. It's a hell of a lot bigger than the Black Hawk slide, and that's one of the biggest I know of in the Mojave Desert. This thing is enormous. Look at the run out. Look how it goes up the opposite side of the Mariner Valley here. That's a lot of acceleration to produce that.
Well, considering the gravity is so low,
Yeah.
not much to stop it.
So mass wasting then is big during the Amazonian. Periglacial activity also starts to become important in the Amazonian. With diminished water, the water is mostly confined to the subsoil area beneath the dry regolith or Martian soil, rocky soil. The interstitial water between these mineral grains in the void areas freezes and thaws over seasonal cycles. So it becomes a very active kind of layer, the subsurface being saturated, the water freezing, expanding 10% of its volume, then thawing again. So this causes the ground to heave and contract under these successive freeze-thaw cycles. Permafrost is underlying the frozen soil and rock below this active layer. And it produces characteristic kind of terrain that we call pattern ground. Here you can see a periglacial region in northern Canada, the pattern ground in Mars. Just these big polygonal areas, kind of like polygonal mud cracks that develop on a dry lake surface, only being the result of the freezing and thawing of interstitial water. Solifluction lobes. Solifluction lobes occur where the soil is saturated in the active layer and sliding over a sloping permafrost layer, typically down a slope. And here you can see solifluction lobes on Mars, and here's solifluction on Earth, up in the Arctic. This is near Svalbard. Approximately same scale, 50 meters. Pingos on Mars and on Earth. Here's Mars. This is a pingo. Here's another pingo.
What is a pingo?
This is Earth. Here's a pingo. Here's another pingo. Pingos are piercement structures, kind of like salt domes, only instead of salt, a salt dome occurs when a bed of salt has been buried to great depth, like 20,000 feet, and under the load the salt becomes plastic and starts to rise and deform the upper lying strata above it, forming what we call a piercement. With a pingo, it's much shallower than that, than a salt dome, but it works in a similar kind of way. It's an ice core that is rising in the frozen soil. It's being fed from the subsurface. Here's another one. So they're hills. They're typically 100 meters, the big ones, in height. Wind activity. Wind activity becomes a very dominant force on Mars over time. It's a desert. Here you can see dunes. Here you can see a dune face. This dune is migrating in that direction. These are both on Mars. Rover images. Vast dune complexes, similar to the sand seas that we see in the Sahara. Another talk I give is on sand and dust on transport on Mars and associated features. Sand streaks. So these are perfect analogs to what we see on Earth. Vinifacts. Vinifacts are rocks that have been sitting on the surface. Sand is traveling, it's entrained in the wind, and it's traveling close to the surface, abrading the surface of the rock until it eventually polishes and produces a facet in the rock. The rock eventually turns over for one reason or another, exposing another face to allow another vinifact to develop. Here's vinifacts on Earth. Here's vinifacts on Mars. Look at that. Wind erosion. Actually, it's the sand impacts doing the erosion. So kind of in conclusion then, looking at a summary of the geologic evolution, the basic history of Mars, the three major eras, the Noachian, the Hesperian, the Amazonian. Here's the pre-Noachian here, first 500 million years. Formation of the crustal dichotomy, the northern lowlands, southern uplands, some of the major basins. Then we get into the Noachian, lots of impacting, major impacts forming these large impact basins. Beginning of volcanism in the Tharsis area, valley networks, those dendritic stream networks that we looked at. Then we get into the Hesperian, rifting, development of Mariner Valley, outflow channels, like those that we looked at, those massive outflow channels, the result of catastrophic floods as the last of Mars's large volumes of liquid water flow out across the surface. Tharsis volcanoes still active, the northern lowlands filling in with sediment, Olympus Mons building in the Amazonian, and then things more or less becoming kind of a fossil relic of Mars's geologic past. What we see today in the late Amazonian is almost entirely a relict landscape. Still a little bit of volcano activity, nothing like what it had been in the past. Some polar deposits, wind, periglacial activity. Producing the present face of Mars. No canals, no nodes, no cities, no Martians. Darn. I remember when I was a kid and the first Mars satellite, what was it, Viking? Or no, it was Mariner, I think. The 60s, I was just crestfallen. Oh my God, no Martians! How can that be possible?
Oh, yeah, Mars cars.
But there's the Mariner Valley.
Well, fortunately, you didn't put Ray Bradbury out of it.
Well, Trump's about to release all the information about it.
Okay.
They're just hiding in the picture.
You have a face on Mars.
Oh, and here we see the southern ice cap and the northern ice cap. Two very visible features from Earth with just small telescopes. The most interesting things you can watch with a small telescope, the waxing and waning of the polar caps, the movement of sand and dust creating what we call albedo features. Occasionally, if you're lucky, you can catch a glimpse of orographic clouds forming on the flanks of these volcanoes.
You had, had a Valley and the Tharsis region,
Yep.
and I would love to see that again, because there was something.
You want to see this area again?
Yeah,
Okay.
there was something I wanted to, and if you're done, were you done?
Yeah.
Okay.
No, she'll start over for you, it's fine.
You want the one with the, you want that one or the one with the map?
Right there. You see that region right?
This in here, that's what they call the chaotic terrain?
This right in there. though.
Yep.
You see that circular region?
Yep.
Last year, they determined it as a shattered volcano. That's, I guess
I believe that. Well, you can see arcuate structure here, another here. I would say it's probably
well, they
two.
looked at that very carefully and did some spectroscopic analysis of the rock from orbit, and it said, yeah,
Yeah.
it's a volcano. So I thought that was
Chaotic terrain. Well, once the hotspot, once the plume activity ceases, it's going to cool and it's going to collapse.
collapsed.
Yeah. The same thing that produces atolls.
Pretty interesting. And when you look at it, I mean, that usually creates a caldera or whatever, but that, I don't see a caldera there, but there are calderas on the other big volcanoes. But the
Oh, this is that's a caldera there, I'm
right,
sure.
But the bulk of those volcanoes are intact.
Oh, yeah,
You know,
because
unlike
this is all active volcanism,
Yeah.
or at least very recently active volcanism. This you can see is all along a rift zone. You can just follow it.
So that one there in the Thars, that one there must be a much older one. Is what I'm thinking.
Let me go back.
So what are the edges of this all from?
These are calderas here,
Right. Right.
vents.
Another thing, when Curiosity first landed, Curiosity rover.
Yeah.
And I watched those photos come up every day. I was just so interested because I mean that was
Oh, I know.
the big rover that had real cameras on.
Oh, yeah.
You know.
Yeah, it was amazing.
And
I think it was around the 4th of July, wasn't it? It was in the summertime.
but anyway, I watched that, and several months into that, these photos came up that showed this outcrop, and it was rounded pebbles, perfectly rounded pebbles, and the outcrop itself looked to me like a conglomerate, and I looked at it, I was like, running water.
Well, yeah.
You know,
There's
running
lots of
water.
evidence of running
And then,
water.
like, 2
It's
weeks
not
later-
running now.
And then 2 weeks later, they came out and announced, we got a conglomerate on Mars.
Oh, yeah.
But that really.
No, running water, fluvial
That was-
activity
that
was
really-
substantial in the geologic past. But it's a very dynamic planet in the past, and it's pretty much a relic in the present. And when are we going to go? I'd love to go, but you know, the chances of any sustained activity are slight because the soil is toxic. It's loaded with perchlorates because of the
But, you know,
tremendous incident radiation.
As far as present life, I think it's probably not likely. But something that's always occurred to me, you know, we found a lot of stuff in, up in the Arctic, in the, what do they call it, the frozen soil, what do they,
Periglacial
the.
environment, yeah.
The permafrost. Tundra. And there is permafrost on Mars.
Oh, yeah.
And up in that northern area where there used to be possibly an ocean. And it just, I've always thought, you know, that possibly in that permafrost, there's if it's microscopic or whatever.
Oh, I
But
think there's
evidence.
no problem
And,
with finding
you know,
water.
We have microbes on Earth that have survived for millions of years. And so my question is.
But we haven't found any yet on Mars. Nothing
Right,
that's
well, I don't think we had the
indisputable.
right equipment
No.
to find it.
But there is water. I
Yeah.
mean, in terms of living there,
Yeah.
there is water in the subsurface. The big problem is the soil. And of course, the
And
intense radiation. I mean, it's basically going to be like establishing a base on the moon.
Yeah.
And everything is going to have to be brought there. And the chances of terraforming it any time in the near future are nil, in my opinion.
I have a question for you real quick.
Yeah.
Is the evolution of the moon similar to the evolution of Mars?
Similar. Let me go back. Let me see. Similar in some ways, different in many ways. I mean, the evolution of Mars, it doesn't have the same tectonics as Earth, okay? But still, the evolution of the Martian landscape is much more similar to Earth than it is to the moon. Because you don't have running water, never have had on the moon. You have no atmosphere on the moon. So all of the exogenic processes that shape the Earth's surface don't work on the moon, with the exception of mass wasting, which only requires gravity. But yeah, this period, very similar all the way across. I mean, we have huge impact basins on Earth that date back to the late heavy bombardment too.
You know, Mercury has a sulfur exosphere or whatever. And that actually extends all around Mercury's orbit. In other words, you can detect that sulfur along that orbit. And there are other moons in the solar system. There are other moons in the solar system do the same thing. Io's one. What they have recently found about the moon is they have identified oxygen on the moon that came from Earth.
Oh yeah.
Now, Earth is shedding oxygen, and it's landing on the moon. That's pretty interesting.
Yeah, Mercury would be more similar to the moon.
Yeah.
Venus is an interesting one. And the tectonics on Venus is extremely an interesting situation.
Gotta go back to the
Yeah.
Venus, I agree. Gotta go back.
Any other questions? That's all I got for you then, folks. Thank you.
So what about the theory that the moon was formed by a collision of a large body in the Earth, and then the eject doesn't seem to be reflected in that chronological theory? Is that not an acceptable theory, that the moon was caused by a collision of a other body into the Earth?
Darwin's theory.
I don't know.
I think Charles Darwin was the first person to suggest that. I think the moon formed like the other planets by accretion and was heavily affected by massive bombardment. But no, Darwin's theory was that the Earth produced the moon. That was his. That some impact cleaved the moon off. And of course, Darwin was even before Wegener, so he knew nothing of continental plate tectonics, or the development of ocean basins and continents, or any of that. So he thought the Pacific Ocean was the basin, the chunk
Right.
that produced the moon.
Well, the Pacific Ocean's too young.
Oh, there's no ocean that's anywhere near that old. Ocean basins are
But
constantly
there is, I
being
mean,
recycled.
The current theory is that, the moon was, created from an impact, a Martian-sized impact that hit the Earth and ejected.
So much stuff.
Yeah. so
Yeah,
much stuff.
but not one big ball. It
No,
just
no,
ejected
no.
so much stuff that it, accretion.
Yeah,
Well, what's really
that's why the-
interesting,
And it was so early. I mean, it's really part of the total
what's really
accretionary
interesting about
process
that
of
whole
the
theory
inner
is,
planets.
I watched the periodicals on this stuff all the time about the Earth impact theory. There's a lot of weird stuff going on in the mantle, in Earth's mantle. And there is what do they call it? A low velocity zone.
Yeah.
Just all beneath Africa and I believe it's India, South America, I believe. And this low velocity zone, and it's chaotic, and it's less dense than the rest of the mantle. And-
Oh, the mantle isn't homogeneous
Yeah.
by any means.
But they think that may be, the suggestion has been made
That it's an
that-
accretionary mass that's buried.
That it's a mass from the original impact. But the other thing that's interesting is the core itself, the inner core itself is very odd because it's linear. In other words, it's crystallized, but those crystals are
You're
linear.
talking about the Earth now.
Yeah.
Yeah.
They're linear. And there was something I read about it that said that might have been an indication that
It's hydrides,
been
I
affected.
think, for the most
Yeah.
part. It's metallic hydrides,
Right. But anyway.
iron and nickel.
Anyway, and but the isotopic similarity between Earth rocks and moon rocks just can't be.
Oh, yeah, and I think you're going to find.
You can't,
You're going to find the same thing. Of course, what you need to look at are the cratons, really. You know, if you look at that, you're not going to find anything like that elsewhere, because all of the cratonic features that form the continental shields are all sialic rock,
right.
and you
Well,
don't
what's
find a
interesting
lot of sialic rock.
What they did find in the lunar highlands is anorthosite. That's really interesting. I mean, I've always wanted to go to the Adirondacks to collect anorthosite.
Oh,
It's such an interesting mineral or rock.
rock, yeah.
But they did, and that's indication that
Oh,
the
yeah.
moon had a crust that was more.
Yeah, there's anorthosites on the moon, and there's, anorthosites here. I mean, it's an ultra basic rock,
Yeah.
though. Kind of like a carbonatite. It's just different. It's not.
Or carbonate.
It's not olivines and pyroxenes.
Well, my favorite volcano is that carbonatite volcano in Africa, the one that's active. It produces white lava that turns gray when it hardens.
Which one is this?
I think it's a white lava. Begins with an N. I think it's on the border with Kenya and Tanzania. It's a carbonatite volcano,
Okay.
and it
Yeah.
produces
Bye.
Thank you.
high carbonate
Yeah.
lava.
Well, that's
Really
all.
interesting
That's a rift system.
Yeah.
Yeah.
That's a really interesting volcano. I think that's the most interesting volcano on the planet. Because it's so unusual.
Did we get any online questions from YouTube Live?
No. Probably 400 questions in there.
All produced by you.
No, we can't hear. Can you turn the volume up?
Didn't get any?
We've come a long way from Percival Lowell.
Oh, yeah.
You know, if anyone's interested, the Astronomical League has a really interesting lunar evolution program shows the whole evolution of the moon in this program. And it's very interesting. We haven't started on it yet, I'm working on the other little programs, but that might be of interest to people. Look at all the different features, and they have a manual on it that goes through everything about the evolution of.
Well, Charles Wood used to do a column in Sky and Telescope every month on lunar geology.
What's that?
Charles Wood used to do a column in Sky and Telescope every month on lunar geology. He would pick a particular feature or area.
I'll have to look at the older.
It's
old
always there,
telescopes.
almost every night, so you can always do some observing, and it's always different every time you look.
Yeah.
And you can see lots of stuff, but it is dead.
Yeah.
Well, I think the most interesting area of the moon to me is what's the name of it? It's the Aristarchus Plateau.
Yeah.
Because that's
People think that they've seen volcanic activity in Aristarchus.
plateau. In fact, the lunar reconnaissance orbiter identified ash deposits up there on that plateau. And that's pretty interesting to find volcanic ash on the moon. I'd like to get my hands on it.
Looks like we got plenty of sundials.
Yeah, I brought a nice stash in case anybody wanted something.
Are we done?
I think we're done.
Well, thank you again. Most
You're very
interesting.
welcome.
Thank you so much. It was really good. Really,
Thank you.
Yeah, it was so informative, and
I was worried I wasn't going to be able to get through all of it, but we made it.
you did great.
Yeah,
Thank you so much.
yeah.